chemistry. All right, let's take a look at section 19.4, which deals with nucleophilic addition reactions. And why is it that carbonyls of aldehydes and ketones, why does a carbonyl make such a good electrophile? Well, there's two reasons why a carbonyl group makes a good electrophile. One is based off of resonance, or one reason is based off of resonance, and the other one's based off of induction. So if we just take a look at resonance, you can see that we have two contributors to the resonance hybrid, right? We have a pi bond between two atoms of differing electronegativity, a carbon and an oxygen, and thus I can draw this resonance contributor here where you really see there's a positive charge right on the carbon here, and that demonstrates why that carbon is electrophilic. If we just think about induction, well, oxygen has an electronegativity of 3.5 and carbon is that of 2.5, so we have a polar bond, and the dipole is going in the direction of the oxygen, which renders the carbon electrophilic. And for these two reasons, aldehydes and ketones are good electrophiles. Well, let's talk about what happens when a carbonyl carbon undergoes nucleophilic attack. It says the carbonyl carbon is attacked by nucleophiles, different nucleophiles, forming a new sigma bond in exchange for the carbon-oxygen bond and becoming a tetrahedral center. And so when the nucleophilic addition reaction occurs on a carbonyl carbon, you go from having a hybridization of sp2 to changing that hybridization to sp3. And so we end up with a chiral center oftentimes. Not always, but we can end up with a chiral center sometimes. Now, you might be asking, okay, aldehydes, ketones, that's what the chapter is about. I get it. They're both electrophiles. I mean, I saw you both, or everybody saw the reactivity of aldehydes and ketones towards Grignard reagents, for example. Well, is there one that's more reactive than the other? Would it be an aldehyde or a ketone? And the answer is here, that an aldehyde is generally speaking more reactive towards nucleophile than a ketone. Why would that be? Well, there's two reasons, and they're not uber complex. The first one is sterics. I mean, an aldehyde is going to be less sterically hindered because it's flanked by an R group on one side, but a measly little proton on the other side, whereas a ketone has two R groups on each side. And the second reason is based on electronic effects. So steric effects, the size of the groups. Electronic effects, well, if you think about what an R group does, do you remember that an R group can donate electron density via hyperconjugation? Well, if you have two R groups in a ketone, that means you've got two dipoles going towards the electrophilic center. They stabilize that electrophilic center, whereas in an aldehyde, you have only one electron donating alkyl group that stabilizes that partial positive charge. Therefore, it's not as stable, and which renders it more susceptible to nucleophilic attack. So aldehydes are more reactive than ketones toward nucleophiles. Well, here's an example of a nucleophilic addition on a carbonyl that we already saw. It says some nucleophiles require acidic conditions, others require basic conditions. For example, a Grignard requires basic conditions. So if you wanted to take a ketone and treat it with methyl magnesium bromide, that has to be done in basic conditions, or there cannot be any acid in there, because we know that if you have a Grignard in the presence of an acid, even if it's a weak acid, let's say you had methyl magnesium bromide in the presence of water, and we went over this in the alcohols chapter, we saw that you're going to end up with methane because this is such a strong base, and then you're also going to end up with hydroxide, and then of course the magnesium bromide, like that. So the carbanion would just rip the proton up, and so we have to be very careful about our reaction conditions for a Grignard reaction. Of course, in the second step, we treat it with water or aqueous acid to add this proton to form our alcohol. But generally, a strong nucleophile means the reaction is going to be under basic conditions. And we're going to really examine that carefully when we talk about different reactions and whether they are run in acidic or basic conditions. So let's take a look here. Under basic conditions, all nucleophiles react with carbonyls using the same general mechanism. This is great news. If you understand whether you're in acidic or basic conditions, when you're looking at a nucleophilic addition, you're always going to be able to apply this mechanism here. So what's going to happen? We have our strong base, our nucleophile. We have our nucleophilic attack. Of course, you have to break the pi bond because we can't have a pentavalent carbon. Then you generate some kind of alkoxide, which undergoes protonation, proton transfer, to produce an alcohol. So the nucleophile attacks, forming a negatively charged intermediate, which gets protonated upon acidic workup. And for that acidic workup, you could choose water, and then here you could also choose H3O+. You know, that would work too. Either one is totally fine. But when we're under acidic conditions, then the mechanism is different. The first step isn't a nucleophilic attack, it's the reverse. The first step in nucleophilic attack in acidic conditions is a proton transfer. Why would that be? Because this is not electrophilic enough to react with an acid. You have to protonate it first to make the oxonium, which is even more electrophilic than a regular ketone or aldehyde. And so now that this is an extremely powerful electrophile, your nucleophile, the conjugate base of your acid, can come in. And so the carbonyl is protonated, forming a positively charged intermediate. Let's go back a slide. Notice that the intermediate that we formed here was negatively charged when we were under basic conditions. And when we're in acidic conditions, we form a positively charged intermediate. And this is something that you want to be very aware of when we're drawing mechanisms, because we're going to look at some complicated mechanisms in this class. Now, this is just rehashing what I just told you, that there's no way you can get the nucleophilic attack of anything under acidic conditions without protonating the oxygen of the carbonyl first to make a very powerful electrophile. Again, this is just repeating it. I forgot that I even had it on a slide. And you can see how, yes, this is an electrophile, but then once you protonate it, you can see that you have a positive charge on the carbon in this contributor to the resonance hybrid. So let's talk more about these nucleophilic addition reactions. Let's see here. Got a reaction between a ketone and HCl. What's going on here? It says when a nucleophile attacks a carbonyl group, the equilibrium depends on the ability of the nucleophile to function as a leaving group. So we know that chloride makes a dandy leaving group. And since our nucleophile here is chloride, it's also a good leaving group. And so the equilibrium actually favors the ketone. You actually end up with more of the ketone than you do this compound here. Well, let's dig a little bit deeper on that and talk about the types of nucleophiles that we are going to encounter in this chapter. So this is what we're going to cover in chapter 19. We're going to see all these different nucleophiles. So today, we're going to talk about oxygen nucleophiles. That's what we're going to talk about in section 19.5. Okay, then we move on to sulfur nucleophiles. 19.6 deals with nitrogen nucleophiles. Then we'll talk about hydrogen nucleophiles, and then carbon nucleophiles. And there's a couple of really interesting reactions. Now you recognize this one. This is a Grignard reagent, so we're going to talk about that. But this is another interesting one here, if you're wondering, what is that? This is called an ylide. And we'll talk all about this. But an ylide is used in a reaction called the Wittig reaction. And Georg Karl Wittig won the Nobel Prize for the development of the Wittig reaction, I think in 1979. So a very important reaction in organic chemistry because it's a new way to make carbon-carbon bonds. But we're going to start by focusing on oxygen as a nucleophile. So without further ado, let's get into section 19.5 where we talk about oxygen nucleophiles. Let's take a look at what they are. I mean, you've got water first, okay? That makes a good, you know, it's a weak nucleophile, but it's still a nucleophile. Then you have an alcohol. And then this one is, you could call it a diol or a glycol. Either one is totally fine. I mean, this is ethylene glycol that's shown here. But, and we'll see other examples of diols, but let's just put that in here. We'll call it just a diol for now. Okay, well, let's talk about this oxygen being a nucleophile. So let's get into it here. And let's do some kind of introduction to how an oxygen containing compound can act as a nucleophile with an aldehyde or a ketone. Well, it says here, if you take a ketone like acetone and put it in the presence of water, it's in equilibrium with what's called a hydrate. So this is a new functional group, a hydrate. A hydrate is where you have, a hydrate is where you have a carbon and you've got two alcohols attached to it essentially. Now, the equilibrium doesn't favor the formation of the hydrate. The equilibrium is actually going to lie to this side, unless you're dealing with a very simple aldehyde like formaldehyde, for example. And the rate of this reaction is really slow unless you have some kind of acid or base. And we're going to take a look at the acid catalyzed formation of a hydrate and the base catalyzed formation of a hydrate. So let's take a look at those. Under basic conditions, we're in, let's say, sodium hydroxide, and you have your simple aldehyde. What's going to happen is your nucleophile is going to attack your electrophile. And then what's going to happen? Well, if you're in an aqueous solution of hydroxide, water is going to behave as your conjugate acid, and then you're going to protonate this alkoxide here, so to speak. So what happened first? The first thing that happened was a nucleophilic attack. However, if we take a look at acidic conditions, the first step is not a nucleophilic attack, because we know that this is not a powerful enough electrophile. And if we're in acidic conditions, we don't have a strong enough nucleophile sitting around. We've got to create a powerful electrophile by doing a proton transfer first. Now you make a mega powerful electrophile, and now water, which is the conjugate base of our acid, hydronium, can come in and act as a nucleophile. Then we just do a proton transfer to regenerate our acid, and we make our hydrate. So you need to know both of these mechanisms. You need to be rock solid on base catalyzed hydration and acid catalyzed hydration. Both of these are very important reaction mechanisms. And if you're saying, oh man, I'm going to have to go back and catch up on these and try to remember them, well, by the time we're done looking at this entire section, I think it'll be a lot more clear in your mind how this works. But this is a David Klein thing. What I have in this slide here, I took it directly from Dr. Klein. This is something that he does in his book. I still have my organic chemistry textbook from 1995, the one that I learned from, and it didn't have anything like this in my book. But this is something that David Klein has kind of learned teaching organic chemistry for so many years. And so I think it's a great idea to take a look at this. Where do students run into problems when they're drawing mechanisms? Sometimes they'll try to draw a hydroxide ion when the reaction mechanism is done in acid. That is a big no-no, right? The rule is this: a strong base is never going to exist if you're in acidic conditions. If your conditions involve like H+, catalytic amount of acid, H3O+, something like that, you're never going to see hydroxide kicking around there. No, it's not going to happen. So just, if you end up with that somewhere in your mechanism, you've gone wrong somewhere. Conversely, if you're in basic conditions, if you're in acidic conditions, the converse isn't going to happen. A strong acid is not going to exist in a basic environment. So let's say you're in, hydroxide, and you draw sulfuric acid, for example. That's a huge no-no. That's not going to happen. You're not going to have sulfuric acid in a basic reaction medium. So you want to keep these things in mind when you're drawing mechanisms. Well, let's get into this mechanism a little bit more and talk about.
Professor Dean,
go ahead.
Would you be able to see water in a acidic environment?
Absolutely. You could see water in an acidic or a basic environment.
Oh, okay. Thank you.
Right? Because water is not a strong acid or a strong base, right? Notice it says you can't see a strong base. You can't see a strong base or a strong acid. Doesn't mean you can't have a weak acid or a weak base. And water is amphoteric. It can be a weak acid or a weak base depending on the situation. Okay?
Okay. Thank you.
Yeah. I mean, it's going to become more abundantly clear, Nick. Like, let's say I gave you this reaction here. Okay? Here's something brand new. We're going to talk about how to make this new kind of compound. It's called an acetal. It's where you take a ketone or an aldehyde, you treat it with 2 equivalents of an alcohol in a catalytic amount of acid. That's what this means here. So catalytic amount of acid. So that tells you you're in acidic conditions. All he's trying to tell you, Nick, is this. If you were to start whipping up this mechanism and then all of a sudden you ended up with this, something is drastically wrong. Like something is crazy. Okay, you can't do that. And it's something that I don't really see students try a ton of, but it's a nice warning to have, just, okay, I can't ever do that. And it can help steer you in the right direction sometimes. So an acetal is an extremely important functional group. It comes up a whole holy host of times in this chapter. It comes up in the carbohydrates chapter at the end of the class. In an acetal, it's kind of like you've got a carbon, and it's almost like having an ether and then another ether on the same carbon. That's one way you can think of it. It's not an ether and an ether. It's called an acetal. But if you want to think about it that way, students tend to remember it that way, and there's nothing wrong with that. So we take our ketone or aldehyde, we treat it with two equivalents of an alcohol and acid, we make an acetal, and we liberate water. Now, if you're wondering, what's this catalytic amount of acid? Like, what kind of acids are you using? It depends. You can use sulfuric acid, just good old H2SO4. But one acid that organic chemists like is this one here, Paratoluene sulfonic acid. Sometimes we call it tosic acid, or sometimes we call it PTSA, so paratoluene sulfonic acid. And if you're wondering, like, well, why wouldn't you just use sulfuric acid? That's everywhere. I mean, it's in every lab. It's great. Well, since you're using a catalytic amount, you don't need a lot. And toluene sulfonic or paratoluene sulfonic acid is a solid at room temperature, and it can be recrystallized if your reaction conditions are very delicate and you don't want any side reactions. You can, make it crystallize it, and so it will be extremely pure, and it just can eliminate, some side reactions, things like that. Anyhow, these are common examples of acid catalysts. I'll bring up sulfuric acid. I'll bring up PTSA, depending on the situation. And sometimes in mechanisms, I might even just draw H3O plus. Depends on the mechanism. Depends on the agents. With all that in mind, let's take a look at a big mechanism. I'm not going to write the word memorize. I'm going to put know this mechanism. The formation of an acetal from a carbonyl, an aldehyde or a ketone. Are you ready? And we're going to go over this one together as a group. But before we do it, there's 7 steps total, right? 1, 2, 3, 4, 5, 6, 7. Now, I don't recommend trying to memorize proton transfer, nucleophilic attack, proton transfer, proton. I don't recommend doing that. I think that the best rationale that I've seen my students use is that the first thing you've got to do is make a hemiacetal. And a hemiacetal is kind of like not an acetal, right? You've got an ether on a carbon, but you've also got an alcohol on the same carbon, okay? That's what a hemiacetal is. So that's your first thing, is you've got to figure out a way to make a hemiacetal. And then the second thing is you've got to make an acetal, and along the way, you've got to lose water. Those, again, are kind of the 3 things that my students I found have had the most success in remembering. So first, you want to start with the starting materials. You want to make a hemiacetal. Then you want to make the acetal, and in the process, you want to lose water, okay? So let's go over it. We know that if we're taking, and what they're showing here is this reaction, okay? That's all that's happening here. So we're taking our carbonyl, I'll scribble it up here if it helps, plus 2 equivalents of our alcohol. We have our acid catalyst, and we're making our acetal. Making our acetal, plus we're losing water. Okay, let's go over it. We know that a carbonyl is not going to be electrophilic enough to react with anything in an acidic medium until we protonate it. So the first step is to protonate to make the oxonium. The oxonium is a wicked electrophile. We already discussed why. So now an alcohol, which is a weak nucleophile, is going to be strong enough to attack that electrophile. And then we get this intermediate, this one right here, which looks pretty close to a hemiacetal. All you have to do is remove this proton. Well, look, after you protonated in the first step, you were left over with the conjugate base. And so that base is going to come along and it's going to rip off a proton, and then you regenerate your acid catalyst. So what's the next thing you need to do? You need to form the acetal, and in the process, you lose water. Where's the water going to come from? It's going to come from here and a proton. So what's the first thing you need to do is add a proton to convert this hydroxyl into a good leaving group, right? Hydroxide is a shitty leaving group, pardon my language, but this is a great leaving group. Water, it's the conjugate base of hydronium. And so now you have the loss of the leaving group and you form another oxonium, which is a great electrophile. So now a second equivalent of the alcohol can come in as a nucleophile, and we end up with another oxonium. You do a proton transfer to regenerate your acid catalyst, and the mechanism is over. That is the entire thing. Now, if that's the first time you're hearing me go through that, or if you haven't read the chapter before coming to class, that's a lot to swallow in one chunk. You know, you say, wow, how am I going to remember all that? Well, the way you're going to remember it is by practicing it. And we're going to get some practice on it in a second. But before we do, I want to show you why the formation of an acetal is so useful and a couple of just little nuances about acetal formation. First of all, you probably noticed that those steps were all in equilibrium. Look, this one's in equilibrium, this one, this. Everything's in equilibrium. And then if you're like, well, holy heck, man, if every step is in equilibrium, how do you even get to the end? You know, how would you do that? Well, you use Le Chatelier's principle to your advantage. Check it out. It says for most simple aldehydes, it's actually the acetal that's favored with something like formaldehyde. However, if you have something like acetone, it's not favored. So again, how do you drive the reaction to completion? Let me tell you. The way that you do it is you remove the water from the reaction mixture. If you remove this, then it's going to push the equilibrium to this side based on Le Chatelier's principle, right? We have a system of equilibrium. If you disturb the equilibrium is going to react in such a way to reestablish the equilibrium. So once it's not at equilibrium, I should have said. And if you're wondering, well, how the heck do you remove water? Well, there's a special piece of glassware that we can use. The textbook doesn't even bring it up. What it's called a Dean Stark apparatus. It's named after two chemists. You don't have to worry about that. The bottom line is we just have to remove water from the reaction mixture, and that's going to push it towards the acetal. Now, what if you use a diol instead of two equivalents of an alcohol, right? In the first example, we used two equivalents of an alcohol, but now we're using a compound that has two alcohols in it, like ethylene glycol. Well, in that case, you end up with a cyclic acetal, okay? And we're going to practice drawing the mechanism so that you can get used to drawing out a cyclic acetal. We'll get some practice on that, and actually not a cyclic, but we'll look at something similar to it in a little bit. So that's it for mechanisms for the next few seconds, okay? I'll give you a break on that for a second. So let's talk about the utility of making these acetals. You're like, okay, Mr. Dion, I follow you on what an acetal is, a hemiacetal. I saw the mechanism. I'm going to practice it at home. Cool. I can do that. What's the point? Why would you want to make an acetal? Well, here is why. Because acetal formation is reversible, it can be really handy. Where did we see something recently that was reversible? Installation of a sulfonic acid, a blocking group. In the alcohols chapter, we saw a protecting group like acyl ether. That's reversible. So check it out. Acetal formation is reversible, and the acetal can be removed just by adding water. Right? It's all based on the concentration. If you have mostly acid and no water, well, and you remove the water, that's going to give you the acetal. But if you take the acetal and just put it in water and put a catalytic amount of acid, that's going to blow it back to the ketone or the aldehyde. And that way, an acetal can be used as a protecting group. So this is really, remember, a sulfonic acid wasn't a protecting group because it didn't mask a functionality, but this is the second protecting group you've learned in the entire course. The first one was acyl ether on an alcohol that we used when we did Greenyard chemistry, and now you have the acetal. Check it out. What if you wanted to do this reaction, or this synthesis, sorry. What if you had a compound, check this out, you've got an ester and a ketone in the same compound, and you just want to make this compound. So you'd say, okay, well, I know that I can reduce an ester. The only way you know how to reduce this to an alcohol is to use lithium aluminum hydride, step one, and then second step would be H2O or H2S, a little bit of acid, okay? Well, hold on. If you treat this with LAH, you're going to reduce this too. This is going to be reduced to an alcohol, so that doesn't work. All right, so what can we do? Well, remember this whole thing about forming an acetal? What was the functional group you needed to form an acetal? An aldehyde or a ketone? I didn't say anything about putting an acetal on an ester or an amide or a carboxylic acid or anything like that. And thus, what we're going to do is we're going to protect this as an acetal. We're going to take this and we're going to convert it into an acetal like this. And then we're still going to have our ester. It's kind of ugly drawing, but we're going to have our ester over here, and then we can reduce that, and then we're going to blow off the cyclic acetal. So first step, we treat it with ethylene glycol and a catalytic amount of acid. We remove water, and again, we use a little special piece of glassware to do that. There's other ways too. You can use what are called molecular sieves, which really do nothing more than just absorb water and prevent it from reacting. Anyhow, then we make our acetal. So this is our acetal. And we still have our ester over here. And the ester is susceptible to reduction with LAH, but the acetal isn't. So what are we going to do? First step, protect the ketone as an acetal. Second step, we do the reduction. And then in the third step, this is one of those double whammies. Two steps in one, right? Not only do we do the acid workup for our lithium aluminum hydride, but we also remove the cyclic acetal. Pretty cool synthesis, huh? Really clever, very clever way of making this bifunctional compound. Now, before we get into a practice problem, I want to address the whole thing about the hemiacetal. A hemiacetal is actually pretty difficult to isolate. The way that we see them, that I showed you in that mechanism that we went over, the 7-step mechanism, it's pretty difficult to isolate a hemiacetal, but there is an exception to this. A cyclic hemiacetal can be isolated, especially when you form a 6-membered ring. So cyclic, so let's put here, especially when you make a 6-membered, meaning 6 atoms in the ring, 6-membered ring. And where would you see a 6-membered ring with an oxygen in it? In carbohydrates. So let's say you have your alcohol and your ketone in the same, compound. Well, then you can form a cyclic hemiacetal. What's a hemiacetal? Again, it's a carbon with a hydroxyl, an alcohol, and an ether on it. And you can see that we have 1, 2, 3, 4, 5, 6 atoms in the ring. And so later on, we're going to look at glucose. And this is just a wedge and dash drawing of glucose. And this is the chair form of glucose here. We won't see this until the carbohydrates chapter. But you see that we have a ring. We have the chair. It has an oxygen in it. And we see that we have a hemiacetal. Where's the hemiacetal? Check it out. Look, it's right here. If we look at this carbon that I'm highlighting in blue, go carbon, oxygen, carbon, so that's an ether. And then you have carbon with a hydroxyl. That's an alcohol. And therefore, glucose has a hemiacetal trapped right inside the molecule. Okay, so that covers oxygen nucleophiles. With all that in mind, let's see if we can't draw a mechanism for the formation of an acetal from cyclopentanone. So we have this dimethyl acetal. Don't worry about acetal nomenclature. It's not part of our course, but we end up with, you can call this some kind of dimethyl acetal. And we're starting it with sulfuric acid and methanol. Now, what's the major acid that's present here? Right, we're combining H2SO4 with methanol. H2SO4 has a pK of -9, so it's going to protonate methanol, and mostly what my acid is going to be will be the protonated form of methanol, and I'm going to be left over with HSO4- as the conjugate base. And so this will be the acid that I'm going to draw in the mechanisms, not sulfuric acid. You could draw sulfuric acid because it's in equilibrium, but again, the equilibrium is going to lie mostly to this side. This has a pK of around -2, whereas this has a pK of -9. So we're talking about a difference of 10 to the power of 7. That's a pretty big difference. Okay? So when we draw the protonation in the first step, this will be our acid. So let's do that. And let's begin. So we'll start by drawing out the acid catalyst, the protonated form of methanol, or the conjugate acid of methanol, whatever you want to call it. And let's put in our lone pairs on our carbonyl. And the first step is going to be a proton transfer. Why? Because there's no way that methanol is a, well, let me try to fix that arrow. There's no way that methanol is a strong enough nucleophile to just up and attack this carbonyl. You've got to create a more powerful electrophile. So let's do that. And remember, we're trying to get to the hemiacetal. So now we've got our oxonium. Now we've got a super powerful electrophile. And we just took some of the protonated form of methanol. It lost a proton. Therefore, now we've got a molecule of methanol. That molecule of methanol is going to act as a nucleophile, and it's going to attack the electrophilic carbon like this. And now we're going to end up with something that's very close to a hemiacetal. It's just going to be the protonated form of the hemiacetal. So we're going to have our OCH3. We still get our proton on here, like that. So now we're only one step away, or one proton transfer away from a hemiacetal. So what's going to be our base? Methanol is our base. So let's draw a molecule of methanol. That's going to rip off this proton, comme ça, as we say in French. And here we have it, my friends. Now you've got the hemiacetal. You're halfway done, or almost halfway done. This is the hemiacetal. So now what do we need to do? Now we're going to lose water, which is going to come from here after this is protonated. And we're going to lose water, and we're going to have another nucleophilic attack. So let's start by protonating this, because you can't just lose hydroxide, right? Nick, if I was to just say, well, this just leaves, then you'd have OH minus, and we're in acid. So that's impossible. I'm not saying that you said that, but it's something that we were discussing earlier. So what's the first thing I need to do is protonate that. Let's draw another molecule of our acid catalyst. And let's draw the proton transfer. This is going to grab a proton from here in order to be converted into a good leaving group. So draw that. So now you've got OH2. This is a positive charge. Now you've got your methoxy group. And here's how the leaving group leaves. The leaving group is not going to just spontaneously leave like that and make a carbocation. What's going to happen is a pair of electrons is going to come down here to make a pi bond, and then our leaving group can leave. I'm taking up too much space with my arrows here, so I'll do it like this. So now we end up with this intermediate. I'm kind of running out of space here, but yeah, oh jeepers, I think I am going to run out of space anyhow. So now we have this oxonium, and now methanol is going to be able to come in as a nucleophile. I'm going to erase the stuff that I have in blue just to make space for myself. Just erase this here. So now methanol is going to come in as a nucleophile, like this. There's my nucleophile, like that. And I'm pretty close to the end now, because I've got my methoxy group over here, and I've got the protonated form of my methoxy group here, like this. And then in the last step, the methanol is going to grab this proton in order to regenerate my acid catalyst. Oops, arrows are getting kind of ugly. There we go. That's good. And that's it. Those are all the 7 steps. Yeah, nothing to it. Yeah, no, I'm kidding. Got step 1, a proton transfer. Step 2, a nucleophilic attack. Step 3, another proton transfer. Then we make our hemiacetal. Now we want to lose water. I didn't write it here, but this is the step where you lose water here, right? It leaves right here. So the next step is another proton transfer. Oops. Proton transfer. Then we have the loss of leaving group here. Then we have a nucleophilic attack followed by another proton transfer, and that is the end. Very important mechanism in organic chemistry. You know, and if you're thinking, oh, I'm never going to remember that, I hope you wouldn't do that. But, you know, just think, it's a back and forth and back and forth. You start with the acid catalyst, you end up with the conjugate base. You use the conjugate base again. You regenerate the acid catalyst. Then it does a proton transfer. You end up with the conjugate base. right? It's kind of back and forth and back and forth and back and forth over and over until you get to the end. So the way that I like to remember it is that I want to end up with the hemiacetal first, then I want to lose water, and then I end up just making my acetal. Give me a thumbs up if you follow me on the mechanism. Is there any questions about this mechanism? It's a doozy. I freely admit that. If I was to say, oh, there's nothing to it, that would be a lie. That would not be true. Okay, so I'm not going to say that. It's not a simple mechanism. It's definitely a complicated mechanism. Well, with that in mind, let's try another practice problem here. This one's a good one. It just says propose an efficient synthesis for each of the following transformations. Here's an old chestnut. I know that everybody here remembers this one. What would the conditions be if you have a terminal alkyne? You have a terminal alkyne like this, but then you want to add an ethyl group to it. Does anybody remember the conditions for that? This is chapter 9, alkynes chapter.
NH2 followed by ethyl iodide.
Exactly. NaNH2 followed by ethyl iodide. What's the problem with that? Okay, let me just go back. There's no problem with that using those conditions. However, if you had NaNH2 here, okay, what's going to happen? You've got Na plus and NH2 minus, and you've got a carbonyl. I mean, this thing is just going to be like, boom, it's going to attack this like crazy. I mean, NaNH2 is a strong enough nucleophile to attack that like stink. So what that means is we've got to find a way to mask the functionality of the carbonyl. Well, the good news is we only know one way to do that. We haven't learned an abundance of techniques for protecting a carbonyl. So let me go over to a blank document just so I have some more room here. Where was I? Somewhere down here after all these cool reactions we tried today. And this is question 19.10. So we're starting out with this ketone that has an alkyne in it, and we want to just add 2 carbons to the end. Doesn't seem like that big of an ask. But again, if we treat this with NaNH2, we're going to get a nucleophilic attack at our carbonyl. And so what do we need to do first? Is protect the carbonyl as an acetal. So we're going to use ethylene glycol, a catalytic amount of acid, and then we always write minus H2O. That tells the reader that we're removing water from the reaction mixture in order to make the acetal. So we have our acetal drawn like this, then we have our triple bond, and now, Caitlin, we can do our deprotonation, can't we? Because there's no reason why we can't treat this acetal with strongly basic conditions. The acetals are very labeled to acid. I told you that, right? All you got to do to knock that off is treat it with aqueous acid. But in base, they're quite strong. And so what do we need to do is what Caitlin said. First step, sodium amide. Second step, ethyl iodide. Let's pencil in what you'd get from that. So we have this, and we have our triple bond like that. And then to knock that off, all we have to do is treat it with aqueous acid. So we'll just put H3O plus. Done. Done like dinner. Pretty neat reaction sequence to make this compound. And let's try the next one. This is 19.10B. 19.10B. Let me just pencil it down here quickly. So we've got a ketone.
Before you move on, or like
yeah.
while you're trying that structure, so at the end of the one that you just did, since we get rid of water at the beginning, if we wrote add water at the end, would that be okay?
Here?
Yes.
There's no need, right? Because when you just write H3O plus, it's assumed that it's a solution of acid and water together. Right?
Okay.
It goes back to, let's say you have sulfuric acid in water. Okay, what is it mostly? It's mostly going to be hydronium and the conjugate base of sulfuric acid, right? Because the pK of this is minus 1.7 and the pK of sulfuric acid is minus 9. So it lies to the side of the weaker acid. So it's assumed that it's just an aqueous solution of acid. Does that help?
Yeah, thank you.
Yeah. I mean, you know, Lindsay, if you wrote like if it was a handwritten quiz or something, or if I asked you to write out the solutions to some answers, and you wrote add water and acid, I'd say, yeah, that's fine, no problem. Just as long as you say add acid, because the acetal is not gonna blow apart in just water. It's got to have some acid catalyst. Again, I'll tell you a little story about that when I stop recording. But acetals are pretty tough in the presence of base. It's just in the presence of acid they fall apart like really quickly. Okay, let's give this one a shot here. Got two functional groups. We've got a ketone and we've got an ester. And if we want to take the ester and convert it into a tertiary alcohol, we actually saw that reaction earlier on in the course. I'm going to go down here and remind you, because we didn't look at it a ton, but we did see it. If we have an ester like this, what we said was if you treat this with excess of, let's just pick a Grignard, or let's just pick R double prime MgBr, okay, followed by treatment with H3O plus or H2O. What you end up doing is you add that R group twice. So you end up with R double prime, R double prime. It adds 2 times to make a tertiary alcohol. And so if we want to add a phenyl, right, that means that we would need, in the first step, we'd need excess phenyl magnesium bromide. And then in the second step, you'd need H3O plus to make this tertiary alcohol. But the problem is, if you treat this compound with Grignard, it's going to react with this ketone. And so we need to mask the functionality of the ketone. What are we going to do? We're going to convert it into an acetal. So we'll treat it with ethylene glycol, a catalytic amount of acid. You could write sulfuric acid if you want. You could write tosic acid if you want, PTSA. And then we write minus water. That's going to give us our acetal, or cyclic acetal. We still have our ester intact. Doesn't affect the ester. And now we can do our Grignard chemistry. 1, excess phenyl magnesium bromide. Step 2, H3O plus. But what did I just say? I said that H3O plus is also going to bust this apart. And so it's 2 steps at once, and that takes you right to the tertiary alcohol. So we'll put here 2 steps at once. Not only do you protonate the alcohol, but you also regenerate the ketone at the same time. Okay, so that covers oxygen nucleophiles. Any questions about those? We'll go back to the slide deck here. And, you know, there's a lot of content in oxygen nucleophiles that we covered, a lot of cool chemistry. So if we go down to the end of the chapter, let's do that. You know, kind of see where we are. I didn't start out with this slide, but this is the review of all the different reactions that we learn in this chapter. And so what we've covered today is we've covered the first reaction, the formation of a hydrate. Then we covered the formation of an acetal and a cyclic acetal. And yeah, that's where we are. That's what we've covered. We've covered the first 3 reactions. In the next section, section 19.6 kind of covers all of these reactions, which are where we're talking about nitrogen nucleophiles. And then it also covers this reaction. This is called the Wolff-Kishner reduction. I don't have the name on there, but that's the name of the reaction. Oops. Not Baeyer-Villiger, that's something else. So let me go back where I was. So yeah, we've covered the first 3, and you can see we have a whole bunch more to go. Another thing is that we can make a thioacetal, and we'll talk about that in a little bit.
Yeah. Why
Go
does
ahead.
the formation of the cyclic acetal, why does it not affect esters?
Why doesn't it affect the ester? Because if you think about an ester, you have an ester like this. An ester isn't nearly as electrophilic as an aldehyde or a ketone, right? You know the reason that we went over why aldehydes and ketones are electrophilic, because of induction and resonance. However, in here, Caitlin, think about it. You've got this oxygen, which can donate electron density into here.
Okay.
Okay, and so that mitigates the reactivity here. It is, electrophilic, but not nearly as electrophilic as an aldehyde or a ketone, right? We saw that it's electrophilic with something that's a super hard nucleophile, like a Grignard, but it won't react under those conditions. Also, yeah, I'll just leave it at that. That's enough of an answer for now.
Okay.
Yep. Later on, we'll talk about hydrolysis of esters, but that's another day.